Good morning, everybody. This morning session, we're gonna be having a little discussion about lagging. One of our favorite topics, isn't it? So let's get right to the point. We all have other businesses to attend to. So why the session on lagging? And I'm not even gonna beat around the bush. I want to tell you straight up what the punchline is that we're gonna get to at the end of this whole session. I'm trying to convince you to make more use of lagging. Why? I mean, we all know the rules about lagging. We know what it is. We know what the law says we have to do, how it should be done. But I want to encourage you to try and use lagging more and more. I mean, I see the non-compliance notices. I see on how many non-compliance notices lagging is just noted as a non-compliance, and it's right. It's perfectly fine. That's how the law works. That's how the system works. As long as you inform the homeowner, you can add it on the notice and so on. But you know what? Lagging is much more efficient on the pipe than on a non-compliance notice. And there's a good reason why we want to use lagging. So if you can, for one thing, look at this slide, load shedding. We all love load shedding, don't we? I mean, it's one of the things our nation spends a lot of money on. I mean, just think for yourself, how much money have you spent because of load shedding? How much money have your clients spent because of load shedding? What do they spend the money on? I mean, what's the cost of a solar water heater? What do you pay for a PV system, a photovoltaic system that gives you electricity when the power is down? I mean, if you really want to be off the grid, to be away from all power failures and load sheddings, it can cost a small fortune. And the question is, yes, even though electricity prices go up and up and up, how long is it going to take you to pay back that amount of expenses, that amount of money that you pay to get those installations? That's for the big stuff. For the small, well, let's move on. I think I've made my point about load shedding. And obviously, you're going to ask at this point, so what? Is lagging going to stop load shedding? You know what? It most definitely will contribute. If you look at Class B geysers, one thing I forgot to say earlier on when I started this whole presentation, and I think it's important to notice, I know that today I'm going to tell you nothing that you don't already know. I mean, all of these things is known to us. It's all the principles that is known to us. And that's why I say it's about what do we make with the information that we have? How do we treat that? And that's why I'm repeating some of the reminders that we know. So back to the geysers, back to the Class B geysers. Do we know that Class B geysers? We know that Class B geysers have been enforced by government in order to save energy. Do you know to what extent? I mean, the fact that if it were calculated that if everybody uses Class B, if all the Class B geysers in the country is changed to Class B geysers, I mean, the country will have to build at least one less power station. It's enormous. It's a massive saving that is supposed to happen just because of that energy saving in a Class B geyser. That's what the project is for. I mean, it's affected all of us, the way that we install. I mean, the bigger geysers fitting through the roofs and all of those things. It's all aimed at reducing energy, reducing. We're not even talking about the emissions, the carbon dioxide emissions that's bad for the planet, bad for our health, and so on. So all of that is part of the process. So just to quickly put it back in perspective, what's that got to do with lagging? If we look at the basics of heat flow, yes, I know, very simple. We know the heat travels from hot to cold. If one object is hotter than another one, the heat will flow from the hot one to the cold one. So if ever there's a temperature difference, heat will travel. And use a cup of coffee as a simple example. When you take the cup out of the cupboard, it's nice and cold. When you take the kettle off well, unplug the kettle to go and pour in the coffee, it's hot water. As soon as you pour the hot water, the hot coffee into the cup heats up. There's been a hot surface or a hot substance, there's been a cold substance. The heat flows from the hot to cold. Now remember, that's basic physics, doesn't stop. No matter where you are, what you have, if there's a temperature difference, there will be heat flow. You cannot stop the heat flow. You can maybe slow it down by different means, but it can never be stopped. It only stops when the temperature is equal on both sides. We also look at the means. What is the basic means of heat flow? How does heat travel from one point to another? And yes, there's a lot more to this. We're not intending to do a science lesson here. But there's two components that's very important within our environment, which is conduction and convection. So conduction is through solid objects. If there's a pot on the stove, that pot has got a nice steel handle. You can't touch the handle, not with your bare hand, because it's heat. That is the conduction. The heat conducts directly through the solid metal, through the side, and if you touch it through the solid flesh onto your body, it's conduction, it burns. Convection is basically when heat travels through a fluid. Fluid could be water, could be air, the steam that travels up, the heat that rises from the pot. That's the convection side of it. And those are the two important things that we need to consider when looking at heat flow in a geyser installation. So example, how does that work within a geyser? How does that heat get lost in a geyser? Remember, the geyser installation is there to maintain the heat. It's one thing to heat up the water, to get the volume of water. It's another thing to maintain it, to keep it there, because as soon as it's there, it will start losing its heat. So in this little image, what I've done is I've made the conduction is red arrows, convection is the orange yellow arrows. So you can see that the insulation of the geyser stops the conductions. It slowed down the conduction of the heat from the water. But as soon that will heat up the outer surface of the geyser. At that point, convection is through the air. The heat is convected, because as long as that outer surface is hotter than the air around it, there will be convection, heat convected into the air. And remember, convection, that is heat loss. That is where the heat is really gone. When it's conduction, it's still within the appliance. It can even still help maintain the heat inside. But the convection is the part that loses the heat. That's a lost energy that goes nowhere and you don't use it. That's where you pay for nothing. You've looked at the insulation material, but on the left-hand side, there are fittings. On this image, we just show the drain cock. I mean, that is a metal part. That metal fitting is in direct contact with the water, so there's conduction. And remember, conduction is much faster than convection. Heat conducts very, very fast through a solid object. It convects slower. So no matter how thick the insulation of the geyser is, the hot water will touch the valve. There's conduction. That whole valve body will be hot, and there will be heat lost through convection. So obviously that applies to all the pipe work around it, all the components fitted to the geyser, all the pipes fitted around the geyser. All of that is the heat is conducted to the components on the outside of the geyser and convected, lost energy into the air. If you look at I think it's worth look at just one little calculation. So this table that you see is in SANS 151. That's the standard for geysers. Sorry. And the geyser standard says that for a 150 liter geyser, that geyser is tested to make sure that it do not lose more than 2.59 kilowatt hours per 24 hour. That's the standard. Remember, this is now the more improved geyser, the class B geyser. not more than 2.59 kilowatt hours per 24 hour. But what does that mean? And yes, I've used a lot of how to say simplification in this whole thing. Electricity prices vary throughout the country. It depends on where on the scale you buy it and so on. But if you use roughly R1.80 per kilowatt hour, it means it costs a household R140 per month. Remember, this is R140 a month just to maintain the water in the geyser, to maintain the temperature. And this is if it's a perfect environment, that's just the geyser body alone, the surface of the geyser alone. Now, if you look at, according to Stats SA, there's some different stats being published all over in different things. There's generally agreed around about 7.7 million households with piped water in the country. And you can take away, some might have geysers, some might have more, some less. Let's just simplify and use 7.5 million households. It means 585 million kilowatt hours per month, 1,000 million rand per month in our country lost just to keep the geyser hot. And this is through the well-insulated geyser body. Understand, this is just through the well-insulated geyser body. Remember, when a geyser is tested, all the pipes and everything is covered, it's insulated. So when the geyser is tested, no heat loss through pipes are calculated at all. So what happens with the pipes and the fittings for that matter? Remember, so this image shows it's a typical infrared image of a pipe. What happens with the heat? You can see the hot pipe on the inside is hot. The red signifies hot, the blue signifies cold. The thicker the insulation, the more it insulates it. And remember, the outer surface is the one that you're looking for. If the outer surface is cool, there's a small temperature difference between the outer surface and the air around it. There's very little temperature loss. There's very little lost energy in the process. We want to get to practical terms. I mean, we don't all have sophisticated instruments in our buckets, in our toolkits to test this and to verify things. So there's a very, very simple test that you can do anywhere you go. And I call it the touch test. Feel, we can all feel. So when you're in the geyser, especially when you arrive on site, when everything is hot, touch the geyser. I mean, go to any installation, whether it's a failed installation or not. Touch the geyser, touch the outer surface of the geyser. Touch the roof structure next to it. Feel the air around it. I mean, can you perceive a temperature difference? How big is the temperature difference that you can feel? Now go and start touching the pipes. Touch the pipes at different positions, at different places. I think I don't have to explain to you that that's one of the things you learn early on. Don't go and touch that hot water pipe close to the outlet. It's going to really, really burn. But go further. Touch the pipe out of the TP valve, going out of the TP valve. How hot is that one? Touch the drain cock. Touch the pipe, the inlet pipe. Feel how far away from the geyser is that pipe still feeling hot. Remember, wherever you can feel a temperature difference, there is energy lost to the atmosphere. Now, for a moment, think about that. The geyser, the outer surface, you can barely feel a temperature difference. So you know there's a very, very little heat loss. That very, very little heat loss cost the country 1,000 million rand a month. Now and we know the pipes are way hotter than that. How much money do you think is lost through that? I mean, the whole Class B project cannot work if the pipes are not insulated as well. There are millions, and this is not exaggeration, there are millions and millions and millions of rands lost in our country purely because of energy lost through pipes in a geyser. And what will it cost at this stage? What's the price of insulation? If everybody fitted a piece of insulation, it would make a massive difference to the success. And remember, never mind the money, load shedding. If you well, the money is important. The money is an indicator of all the other efforts that goes into that. It's an indicator of the amount of CO2 in the air that we're breathing. Let me not carry on about that. Let's look at the next topic: freeze protection. I mean, this is obviously a different, another reason. Some parts of the country more important than others, but large parts of the country it is very, very important. The question is, how does ice cause a pipe to burst? And have you ever wondered, why does the pipe always burst in the middle? Everybody keeps going on about making sure the pipe is sealed from end to end and all the corners and everything. But the burst is not there. The burst is in the middle of the pipe whenever you have a pipe burst. Most of the times in any case. Why is that? So again, simple basic physics that we all know. We know liquid, if you cool water down, it becomes ice. If you heat it up, it becomes steam. So what happens with the ice? And look at the structure of the molecules at the bottom. Ice takes up more space than water. So when it's water, the molecules are flexible, close to each other. When it turns into ice, those molecules are rigid, and that's why it takes up more space. Why do we care about that? Use the example in a pipe. Above 0 degrees Celsius, the water is water and there's no issue, obviously. Now just imagine for a moment the pipe at the bottom. Now it's below 0 degrees Celsius. For some reason, ice started forming on the one end of the pipe. On the left-hand side, ice started forming. Remember, this ice, when it forms, it now starts taking up more space. What happens? It starts pushing the water out the other side. Water's got to go somewhere. Going to the next slide. So what if a little bit of ice formed on the one end of the pipe and a little bit of ice formed on the other end of the pipe? Now suddenly you have a blockage. Now that ice will keep on growing. It will keep on taking more space. What happens with the water in between? The water pressure in between these two pieces of ice keeps increasing, and that can keep increasing to the point where the pipe can't handle the pressure anymore, which is why the pipe tends to burst in the middle more than on the sides. So again, I simplify, there's more science to this. Repeated icing weakens it, weak spots burst easier than others. There's other things that can play a role. This is the main reason why pipes burst due to ice in general. What's the vulnerable areas? And I think this is where a solar water heater is one of the more important ones to look at. We've heard about a lot of solar panels, the collectors that burst, and we tend to think that it is the ice expanding inside that little pipe, but that's not really the case. I've circled the areas there, well, rectangular circles, if you want to call it that, the vulnerable areas in the pipe that has to be insulated, because that's the areas where the ice form. If the connection, be straight, if the connection to the panel is not insulated properly, if that's exposed, that's where the ice is going to start forming. And what's going to happen? If the connection to the pipe freezes on the one hand and it freezes on the other hand, it's like closing the valve. It's sealed. Now that ice starts expanding. It starts pressurizing the panel throughout the whole panel. And where's it going to go? Somewhere in the middle of the panel. So that panel didn't burst because it's a bad panel, or because there was a weakness on the pipework inside the panel. That panel burst because the fitting on the ends were not insulated, because the fitting on the end caused ice to form and to cause a blockage. So some simple examples about vulnerable areas, things that we've seen. If pipes look like this, obviously you have a vulnerable spot. Ice is going to form at that point, and heat is going to be lost to that point. The materials has deteriorated in the sun, so the conduction value, or the resistance that it gives to conduction is reduced. So a lot more energy will be lost there as well. So this is one of the realities we gotta face. Insulation outdoors need maintenance. You cannot get away from that. There's a lot of information available about maintenance and a lot of opinions about how and what and where, but don't leave it like this. When it gets to this, do something about it. Just another example. Sure, I don't have to explain too much about this. You can see how that is going to cause some serious challenges. It's all about maintenance. A quick reminder, what does the standard say? We know that it's a legal requirement to comply with the standards, and hopefully you'll understand the reason for this. So a simple reminder, SANS 10252 part 1, just go back, write this down, open your standard, go and read up again on it. Clause 6.7.5, thermal insulation, it explains everything there. I've just highlighted 2 simple things in there. One of the important things, we know it must be R1 lagging, not going to talk about that, but it must be the hot and cold water pipes that needs to be insulated. All exposed pipes to and from the hot water cylinder must be insulated. We've noticed that we've highlighted all exposed pipes must be insulated. Remember, the heat loss is not only for the hot water pipe. The heat loss is also for the cold water pipe, the conduction that goes to the cold water pipes. Just a little bit further down the line, 10252 part 1, clause 6757, where it says the cold water supply piping within 1 meter of the container, and the hot water must be the full length. It also says the cold water, it highlights the fact that even the TP valve, the discharge pipes from the TP valve needs to be insulated. And for all practical purposes, even though the standard isn't explicitly saying cover the valve as well, because that is a point of heat loss. The more you reduce the exposed areas, the better the protection that is there. That's all in the standards, and as I say, we all know that already. So, what do you say to the homeowner? It's good and fine for me to say use more, use more, use more. It's not you that make the decision. We know it's the homeowner that make the decision. How do you approach the homeowner about this? How can you contribute to? You want less load shedding? Convince all the homeowners to fit lagging everywhere so that you can have less load shedding. We know that homeowners, nobody will pay for something they don't understand. If they don't see value in it, they will not pay. But if they can see the enormous value in paying a little bit, they are much more likely to pay for that. So explain to the homeowner the advantage. Teach them my experience, the touch test. I've spoken to so many people say it's simple. Heat travels from hot to cold. Touch the geyser, touch the pipe. What do you want to do? And in most cases, that alone make them understand, give them at least a appreciation of the importance of lagging, and offer them the lagging. Try to convince them rather to fit it. As I say, lagging is much more effective on a pipe than on a non-compliance notice. The other recommendation somebody made the other day says, consider this. These heat sensors, heat guns, becomes much more cost effective. You don't even need a very expensive one. Lately, they're available under 4,000 Rand, lots of them. A lot of them you can get on the cell phone contract. It's part of a cell phone deal and so on. Imagine for one moment getting into the roof when you arrive for the work. Often everything is still hot up there. Take a photo, take an image of that, bring that back to the homeowner and show them. Look at the hot pipes, look at the cold areas, see where your heat is lost. Sir, ma'am, don't you want me to fit a piece of lagging for you there and you can save some energy? Consider that. That's one of the practical tools that you can try to use. So in conclusion, we all understand lagging, we know that, but we have to sometimes remind ourselves, it's not always about the individual case. I mean, use nature as an example. I mean, ants work together as a colony. As a colony, they achieve a lot of things. It's like a voting system as well. If everybody, if you don't vote, it contributes to the overall result. If everybody contributes, if we all at least make an effort to convince people to rather fit lagging. Imagine for a moment that lagging could be fitted, that we could convince the whole country to fit lagging. We will immediately have less load shedding if that's your motivation. All the health benefits and everything that it brings. I think it is really, really worth the effort. And it just confirms that there's been a good reason for putting those requirements into the standards.